Okay, we're good. All right, let's see, anyone homework? If you've got them, throw them up. If not, I'll see you at 6 with the homework. Let's see, I think I pushed the solution set for the last homework already up, and tonight I'll push the one for this up. But if not, someone pop me an email and I will do so. It's worth looking at the solution sets only to determine what's going on. All right, a few things that are of importance here. One is that we have a room for our midterm. However, I don't exactly remember what it is, so I'll post it up on the website. But it's not going to be in here. I think it's going to be in Kresge 123, but I asked for a cavernous room so we could all spread out. So it's going to be the 14th, 12 to 145, and I believe it's going to be Kresge 123, but check on the website. Right, this is suspect. All right, so as soon as I can get to my email and do that. What's that? Yeah, it'll be open book, open notes, no MATLAB. All right, so I want you to learn how to do this by yourselves first, and then you can. Huh? Not as a program to find roots and do a root locus for you. I mean, you know, no MATLAB in spirit, not just in like if you can program your. That's, I mean, factor is fine. That I don't mind so much, but definitely, you know. Besides, then all I do is just leave it symbolically, and you guys have no hope anyway. So. But what? Oh, okay. Well, there you go. The things I didn't have to deal with before. All right. There was one. I kind of want to do an example here, just to see what we're gonna do. And so we'll do this example. Then I'm going to go back and go through and do a. And then we'll continue on our root locus extravaganza, get to the rest of the rules, and start going. Okay, so I really need to write down which order these come in. So, I think this is right. Okay, so let's see. Example I've got is, so I have a system where I want to put this compensator in it. Okay, it gets a disturbance from the outside world, and it's a fairly simple plant, but it's a simple plant that I have already wrapped a feedback loop around. So here's my plant. I have a gain that comes back. And then, so this is sort of a typical example of where this comes along and you say, well, I have some system that already exhibits some closed loop. Someone already wrapped a control system around it for me, but I don't like it. I don't like the way the whole thing performs, so I say, hey, I'm going to be clever. I'm going to come around, I'm going to wrap another control loop around it afterwards. All right, this is often referred to, by the way, as successive loop closure. Very common way they did autopilots in the past was they said, well, I'm going to make something that levels the wings, I'm going to make another thing that holds altitude, I'm going to make another thing that will hold a constant bank angle, et cetera, and then I'm going to wrap all the outer loops so that I get to actually follow the course that I want on top of all of those. All right, and it can have some interesting aspects. This is one of those cases where optimizing every one individually is not the same as optimizing the whole together. And if you optimize the whole together, sometimes you want to actually destabilize one of the inner loops and then restabilize it with the outer one. So there's some issues that come up. Anyway, the thing I want from this one is I want a steady state error to a ramp input to be some constant. All right, so that is a type what system? Type 1, right? Okay. All right, so if I look at this, the first thing I'm going to do is collapse this inner loop, right? And that inner loop is going to look like a 1 over s squared with a k, right? So this inner loop is going to look like what? So it's 1 over s squared over 1 over s squared, 1 plus 1 over s squared plus k, right? Times k. Right, and then I multiply it up, and this is going to be 1 over s squared plus k. Very quickly, where are the roots of that? Right. Well, assuming k isn't 0, right? They're always imaginary, right? Which means that this system does what? Pure oscillation, right? So this is a pure oscillator. Okay. So now I take my system and I say, okay, I'm going to rewrite it from here. I've got my reference input. I now have my compensator. I have my world disturbance pushes in. And I've got my 1 over s squared plus k. And I go out to y, and I have my feedback. Okay. So now I can say that, well, if I want to do y over r, all right, so I want to know how well I track my reference. All right, so here's r. Okay. This is going to be d over s squared plus k divided by 1 plus d over s squared plus k, or d over s squared plus k plus d. Right? So far, everyone with me? Okay. And if I say, well, this tells me how good I am at tracking my response. What I'm really interested in is how much do I attenuate my disturbance. Right? So I actually want y over w. Right? So y over w is going to be, right? So I'm going to go, this for the feed forward path is going to be this thing right here. I do have the pointer on, right? Yeah, okay. So it's going to be from w to y is the feed forward path. So this is 1 over s squared plus k. And then I've got in the feedback path 1 plus d over s squared plus k, which is going to be equal to 1 over s squared plus k plus d. So again, same denominator, very different numerator. All right. Okay. So the other thing I can do is I can say, well, all right, if I want to write what my my y of s is going to be, all right. So y of s is going to be equal to, I can write it this way. I can write it 1 over s squared plus k times w of s plus d over s squared plus k times r of s, all over 1 plus d over s squared plus k. Right? Important to note that the full response is both, it's the sum of what I get from my world disturbance plus what I'm asking it to do. Right? I get both. Right? So often we'll say, well, set this one to 0. This is just linear superposition. Right? Okay. So, and if I want to look at what my error is, my epsilon over my reference. All right. So if I go back, this is now that point right there, right, that I'm looking at. So now I get 1 over 1 plus the loop gain. Right. So this is going to be 1 over 1 plus d over s squared plus k, which is equal to s squared plus k over s squared plus k plus d. Right? And what I want to do is I want to know E of S given that R of S is equal to a ramp. Right? So this is equal to S squared plus K over S squared plus K plus D times 1 over, well, I'm just going to, let's do this, times R of S, and R of S is equal to a ramp, which is 1 over S squared. All right? And then, so I've got the E of S is equal to S squared plus K over S squared plus K plus D. Right? So far, nothing more than just a little relatively simple algebra to get me here. And now I want to know what is epsilon of infinity or epsilon of steady state. Right? And the way I do this is I solve this with the final value theorem. Okay. Now, what do I have to be careful of here? Right. So I have to be careful here because I'm on the, if these are purely oscillatory, right, I'm on the limit. Okay. So I just have to be careful here. All right. So the way we're going to do this is we're going to say that epsilon of steady state is going to be the limit as S goes to 0 of S E of S, which is the limit as S goes to 0 of what we had before, except now I'm going to multiply it by an S. Right? So I'm going to get, this is the limit of S times, so it's S over S squared, and I've got S squared plus K all over S squared plus K plus D. Right? Now, this right now is going to go to what? Right? I cancel this one. Right? This one's going to blow up. Unless what? What if D, so right now we're assuming that D is just a constant. Right? What if instead D is equal to D of S? Right, but if D is a function of S, I can get another S up there. Right? So let's say, in other words, D has to be, in order for this to have a finite value, okay, it's telling me I have to have D is equal to some numerator, denominator, right? And it's got to have a free S out here in the denominator, right? If it does not have a free S in the denominator, we're stuffed. Okay? So let's say that I'm just going to take this form. It's going to be, so we're just going to say that D is equal to 1 over S N over D. All right? So this is D of S. Okay? So now, as long as I put that in there, all right, so this is going to be, and in fact I can put this at, so if this has a free one in it, then the steady state is going to be, the steady state of this is going to be wind up, so E steady state, if I have this form, right, what's it going to wind up being? K over what? K plus, it's K over N over D. Is that right? Yeah. Okay. Evaluated at equals 0. What? It's KS? No, that's right. Right. It's got killed. Okay. So this is what we're going to have left. All right. Evaluated at def equals 0. All right. So basically, as long as I make D in this form, I'm okay. All right. So if I gave you the spec, right, on this system back here, I said, okay, here's my, actually all the way back here, right? So I gave you the spec that to a ramp input, all right, I want a constant disturbance, all right, which means, by the way, I could also say that to a step input, I want 0 error, right? And in order to accomplish that, it told me I'm not entirely free in my choice of D. Right? There are constraints that this imposes. Right? So in general, by the way, if you've noticed on some of the problems in the homeworks by now, we always sneak in this steady state error spec, where you say, well, make the steady state error less than 10%, or make it something like that, which constrains the design. All right? This is where we're putting in effectively what is a tracking. The steady state error, all right, is actually a tracking spec. It's not a time domain spec. Right? And what it does is it dictates how big some of your gains have to be. Okay. So, for instance, if I now say, well, what's my error to a disturbance? Right? So this is my error based on a tracking input. Right? But now I want to know, I say, well, I want to know what my error is based on a disturbance input. Okay? So this is equal to -1 over s squared plus k divided by 1 plus d over s squared plus k, right? Which is equal to -s over s cubed plus ks plus n over d, where d of s is equal to, again, n over SD. Right? So that's a D of S in there, just to be. I'm overusing my D's. Okay. So now, if I say, hey, if I now want my steady state error, right, to a disturbance input, this is now the limit as S goes to 0 of S E over W of S times W of S. So this is the limit as S goes to 0 of minus S squared over S cubed plus KS plus N over D. Right? Times whatever W of S is. Okay? So this means that for W of S is a step, right? A step on the disturbance gives me 0, right? And a ramp gives me a constant. All right? Now I say, that's great. What kind of compensator looks like that we've been playing with, right? Within the, let's just go and say within the PID family, right? Just an integrator? Proportional plus integral, right? Generally, you almost never use integral control alone. It's always proportional plus something else. All right? If you wind up using just integral gain, you get very, very strange responses. Now, that sometimes can be useful, but not often. All right? It's generally that's where you're trying to drive something, for instance, and you're not concerned necessarily about saturating the output, but you have a rate limit on your actuator, and so you need to take care of where that happens. So then you'll say, okay, well, let me put as my control input not the thing itself, but the derivative of the thing itself, and then see what happens, and I can set bounds on that. All right. So let's, for giggles, we're going to choose D of S is going to equal to KP plus KI over S, right? And this is going to equal to SKP plus KI over S, and lo and behold, I've got something in the form of something that I want. All right? So now I go back and I say, okay, so what's Y over R equal to? So Y over R in this case is D over S squared plus K plus D. All right, well, this is now going to be S squared plus K plus SKP plus KI all over S, which is equal to S cubed plus K plus P, let's see, all right, K plus KP times S. Why do I have a plus 3 in here? S plus K plus KP plus KI. Right? Did I get that right? All over S. Well, right. And then that S is going to go up in the numerator. Right? So this is and so this is going to be KPS plus KI. Right? Now, this is kind of interesting. All right? So I now have so what's the problem here? Right, with this S cubed? Does everyone see what the I'm going to make a bold statement that this is unstable because there's a 0 term on the S squared, right? So as much as I like that, right? That got me my steady state response. It did not get me a stable system, right? So I'm hosed. So I say, okay, no problem. Let's roll out the big guns. We're going to go for PID control. Hey, all right. So now I'm going to have KP plus KI over S plus KD times S. All right. So doing the same analysis, I've got that delta S is going to be S cubed plus KD S squared plus K plus KP S plus KI. Now, how would we figure out whether or not this is stable or not? Ruth, right? So here we go. All right, so when you see something like this, this is the time to roll out Ruth. Say, all right, what limits do I have in MATLAB? Yeah, of course. MATLAB will do everything. There is no question. However, MATLAB will not save you on the midterm or the final. So MATLAB will not do that. So therefore,
there's also a design autopilot program where you just show a picture of a plane, designs an autopilot for you.
It's coming. Let less do you think. All right. So we've got S cubed plus KD S squared plus K plus KP S plus KI. All right. So we're going to set up the Ruth array. So we start. So here's going to be the S cubed, the S squared, the S, and 1. All right. So I'm just going to go through, and this is 1. Skip K plus KP. Right there. All right. And then, so skip, 0. And then the next one, this is going to be KD. Right. Skip KI and 0. So I need the determinant, negative the determinant of 1, KI, K plus KP, KD, divided by KD. Right? So that's going to be KI minus KD times K plus KP divided by KD. So minus Ki plus Kd times K plus Kp all over Kd. And the next term that goes right under this column is 0. Right? And then the last one I need, which goes right in there, all right, is minus the determinant of, well, this is actually kind of interesting, right? Because it's that times that minus that times that divided by that thing. So all I get here is Ki. Right? Does everybody see this, or do I have to write it out?
I think we're divided by KD, not by that thing.
No, for the one that's down here, right? So this is minus the determinant of Kd, Ki, 0, minus Ki plus Kd, K plus Kp all over Kd, divided by minus Ki plus Kd, K plus Kp all over Kd.
I think
You always divide by the...
by the top left and the determinant.
No, you divide by the bottom left in the determinant.
Oh, this is wrong answer to my homework then.
There you go. Still time to retrieve it, to redo it before... before. Okay, so this is Ki in here. Nope, because the minus cancels out, right? Because it's going to be minus that. It's minus that term divided by that. Okay, so it's positive Ki. Okay, so now we say, hey, great. What is this? Now, there's a couple of things I know from here, right? I can tell you that Kd has to be greater than 0, and that Ki has to be greater than 0, and that K plus Kp has to be greater than 0. Right? So I already knew those just by examining the necessary but not sufficient condition of the polynomial. Right? So now I can, and those are, if I look at this first column, those are, well, Ki is greater than 0, Kd is greater than 0. All right? So really I've got to look at this one. Okay? And that is that, what do we got? I've got that Kd is greater than 0, Ki is greater than 0, and I've got that minus Ki plus Kd times K plus Kp all over Kd has to be greater than 0, right, for me to get stability. Right? And what that gives me is that K plus Kp is greater than Ki over Kd. All right? Or the last one is that Kp plus K minus Ki over Kd has to be greater than 0. So here are my stability criteria. All right? So if I get that stability criteria, I automatically get my steady state performance, right? Because I have that free S in the denominator. Right? So as long as I have that free S in the denominator, I'm okay. Right? Did I confuse the hell out of you guys? Is this actually useful? Yeah? Okay. All right. Let's see. Let's see. We've got another one. Let me do one more example, and we'll launch back into to the quickie. All right. So I've got a closed loop system, which is B naught S plus B1 over S squared plus A1, oops, not AI, A1, S plus A2. Okay? And let's see. So I've got something of this form, and I want to say that T rise is less than 0.1 seconds. T settle is less than 0.5 seconds. And MP is less than 20%. All right. And, because we always throw that in there, E steady state to a step is equal to 0, and E steady state to a ramp is less than or equal to 0.001.
Is the settling time a 1% settling time? Or?
No, the settling time is 0.5. It's the standard 1% or 2%, whatever we used. Okay. What did I give you as the standard?
1%.
1%. Yeah. Okay. So we know that T rise, right, is approximately equal to everybody. Is it 4.6 over omega n, or is it 1.8 over omega n? No, it's 1.8 over omega n. You guys got the other. That's the settling time. This is 1.8 over omega n. All right. So this means that omega n, right? If that's 0.1, omega n is greater than or equal to, right? 0.1, 1.8, 18. Okay. I've got that T settle is approximately 4.6 over zeta omega n, right, or sigma, if you want. So 0.5, plug it in, that gives me that zeta omega n is greater than or equal to, what is it, 0.45? No, 9.2. Okay. And lastly, the maximum overshoot, right? This is equal to approximately e to the pi zeta over square root of 1 minus zeta squared, right? And minus that. All right, and this gives us that zeta is greater than or equal to 0.45. Okay. So from here, from these specs, right, I want to draw. So what I want to know is basically how am I going to solve this? All right. So in this case, all I'm doing is factoring polynomials, right? Here's the form of the closed loop. I'm just picking A and B, right, in order to get me where I need to get. Okay. By the way, out of curiosity, which spec affects A's? Which spec affects the B's? Do they all affect the A's?
Well, the right side is going to affect the B because Wn goes on the numerator in the final form of the equation.
Well,
You have Wn over Wn squared plus 2
not necessarily, right? This is omega n squared is there, right? And this is zeta omega n. Okay, so these three only affect those two. Okay, what affects this? What does the numerator give you? What do the coefficients of the numerator give you? Anyone remember? Did I not have you guys do enough partial fractions? Clearly, you need more. Right? Remember that when what the numerator gives you are the residues. How much of each of the response you get? No, it's not going to be zeta, right? They're going to be, the characteristics of them are going to be set in, the characteristic is going to be set entirely by the A1 and A2. Where it settles out, however, all right, is going to be affected by the B's. All right?
These also kind of affect the rise time?
Nope. They do not. Right? Because all you're looking at in the characteristic form, you're saying, look, this is going to tell me where to place my poles. Okay? Where to place my poles tells me what the characteristic dominant second order response looks like. But it doesn't tell me how much I mix each of them.
I thought you get some kind of phase delay or something.
You will, but it doesn't come into in our first order analysis, we assume we ignore what the numerator is. Right? So this is just something to be careful of, right? So this is sort of the classic thing that young control engineers fall into, right? Is you do a root locus design, you put your poles exactly where you think they should go. All right, and you pat yourself on the back and you say, I did a great job on this one. All right, and then you go through and you run it and you get nothing like what you expect. And you say, well, but I put the poles where they were supposed to go. What happened? All right, and that is that this is why we introduced these. There's a whole bunch of tracking response that you need to do as well. All right, so in this case, I just want to draw sort of where the acceptable regions are. So the omega n, right, says I got a radius of 18 here. Right, that's my omega n spec. My settling time spec, rather, this is my rise time. This one crosses here at 9.2, right? And this is my settling time. All right, and then lastly, I have my, of course I put them right on top of each other. This is sine of 0.45, right? Or rather, this is arc sine of theta is equal to 0.45, right? So let's say I say, hey, I'm gonna find my spot, right in there. Okay, they're supposed to be symmetric, but I can't draw. So, there's my spot that I want to do. All right. So, in fact, I'm going to be bold, and I'm going to say, look, I know it's got to be the sigma part's got to be greater than 9.2. Right. And I know that this omega line, I can actually figure this out where it has to be. Right. I can figure out this intercept right there, and I'm just going to put it right above it. Right? So I'm going to say sigma is going to equal to, I'm going to choose my two poles at s equals 9 plus or minus 17j. Right? A nice, yeah.
I have a question.
Yeah.
Just kind of an aside, when you draw this kind of diagram, sometimes the zeta is such that the sigma doesn't really appear. Does
Correct.
that tell you anything about your system?
No, that only tells you that your settling time, that to achieve your settling time, you've already got, hold on. If your zeta doesn't appear, your zeta will always appear going out, but sometimes your omega n doesn't because this slides too far out.
So, well, like in this example, for example, when you have the zeta crosses right at the point where...
Right, when zeta crosses right at the point, it says in order to, if I match my overshoot specs, okay, I've already matched my settling time specs because they're related.
Okay.
Right. And if I don't have a lot of overshoot, I don't have a lot of ring for a second order response. Right. So therefore, they are of course related.
Okay.
Right. And you can see that because as I fold this down, of course, equivalently the line is projecting farther down. Right. If I do that one and I choose that point, then there's the settling time spec. Right. Is going to be there, which crushes that one. So merely by rotating the line down, if I meet my rise time and my overshoot spec, I've already met in fact, I'm going to settle faster than my settling time spec. Okay. So I pick this spot. All right, and I say, okay, I can find A1 and A2 in order to meet that. How do I determine whether or not I've met my steady state? Right. What do I need to do? Right? I need to find E over R and apply the final value theorem. So I take the limit as s goes to 0 of s E over R times my R and make sure I'm okay. Right? And if I'm not, then I need to go back and probably design that will tell me whether I can meet it with something of this form. And if I can, great. And if I can't, no biggie. Okay. Let's see. All right. That one's there. Let's get back into the world of root locus. All right. Any questions about sort of that? Because these are sort of fairly typical problems. Yeah.
So
Eric.
when we draw this diagram, I'm trying to figure out how this relates to when we draw all the poles out.
Okay. So let's assume for a minute I have a system that looks like 2 poles at the origin, all right, and a 0 here, and, well, let's leave it at that, okay? 2 poles at the origin and a 0 here, okay? Based on my rules that we know already, okay, so I know how to handle the 0, how to handle the real axis, right? And that is, to the left of an odd number, the root locus exists. Anywhere else it does not. Okay? So here, I've got 2, doesn't exist. To the left of an odd number, I've got 3 here. Okay? It exists. So there's a root locus that goes from here out to infinity. Okay? Now, what you will learn later today is that these 2 split off at 90 degrees, orbit around, come back in here, 1 goes to the 0, 1 goes to the pole. Okay? And that's not hard, and it's not a big deal, but we'll get there. All right? So one of the things that says, okay, so here is my system, all right, and I now know what the root locus is like, okay, for feedback. All right? So this is a system that looks like an S minus A, or rather an S plus A over S squared. All right? That's my plan. Right? That's the S squared. That's the S minus A. Right? And I say, putting this in feedback, right, and with a gain K, doesn't really matter whether the K is here or up there, makes no difference. Right? But putting this like this and flipping, twiddling the unity feedback, the feedback that I have here, I can take these 2 poles, move them on this arc around. They're going to orbit the 0. They're going to plug back in. One's going to go towards, one's going to go away. And you say, okay, here's my system. Here's what it does. And now I come along and I say, okay, to make the system useful, right, I need a rise time. I've got a settling time. I've got an overshoot spec. All right, maybe I've got a steady state to a step that I'm looking for. Maybe I want a steady state to a disturbance, which comes in here, all right, to a certain amount. All right. And now you say, wait a minute. All right, these 3 are going to define regions here. Okay? The rise time is going to say, look, stay out of that area. Okay? The settling time is going to say, maybe I've pushed for settling time, so it's more stringent than the rise. All right? And then I've got an overshoot spec, and it says, look, here's your overshoot spec. All right? So the remaining regions in which I'm allowed to put my control, right, is going to be, I need my poles to line up in somewhere in this region, okay, over in here. Okay? So now, but I know where the poles go, right? So I say, okay, well, this is all the possible locations that I can move my poles to, right? So, all right, well, how about right there and right there, right? As soon as they cross in the boundary and satisfy my overshoot spec, right? Okay, so carefully, as I crank up my gain, right, the poles are moving, right, and they're moving symmetrically. Symmetry always applies, right? As soon as I cross this boundary right here, check, rise time spec is met, okay? But it's way too oscillatory, way too much overshoot, right? As I keep cranking it around, I get to this point, right, and I say, okay, I just met my settling time spec, right? But I'm still got too much overshoot, right? Keep cranking it around, and the overshoot starts to decrease, and I pick my spot here and here, right? And I say, okay, how do I find my gain to put me at that spot? Well, pick a spot, all right? There it is. I've got the length to there, twice the length. I've got this length divided by twice that length, or that length squared rather, right? And that's it. That's K. Done. All right? As you can see, not hugely difficult. All right? So there's a lot of intuition buried in here. All right? So the intuition buried in here is knowing what the response looks like as I'm moving around. All right? And then combining this with the root locus. So let me just be sort of super pedantic, but also slow this down so it's clear. I now understand anywhere in this region what the response looks like. I pick here, I've got an exponential growth with an oscillatory envelope. All right. I pick here, I've just got an exponential growth away. All right. I pick here, I've got a pure oscillation. I pick here, I've got a damped oscillation. Right? I know what all these responses look like. All right. So I now understand that wherever my roots fall, I know how they contribute to the overall system response. Okay. I also know, based on some simple approximations, all right, how to relate my settling time, my rise time, and my overshoot specs into regions of the S-plane that are acceptable. I can now say, hey, I know how to take time domain and map it into my complex plane, right, and give myself essentially keep-out regions. Right? So step 1 is I know how it responds. Step 2 is assume that it's a second-order response and map time domain specifications back into the complex plane. Step 3 is add the root locus in, and I now know what the constraints are of the motion of the poles. Right? I know everywhere that the poles can go. The poles of the closed-loop system are always somewhere on the root locus. Okay? They can't get off the root locus. All right? That's it. This is the whole possibility of where they can go. All right? So if I have 2 here and 1 here, by the way, okay, this is going to be a different one, right? This one's going to do this, right? So I still got that one heading off to infinity, but these two are actually going to wind up branching up and going on to an area this way, all right? And they're going to hit on that, and those will be 60 degrees apart, and we'll see why a little later. But the point is, I look at this and I say, I can't do anything here, right? Why can't I do anything here? Well, not with negative feedback. Turns out I can say, well, I'm going to get really dangerous. I'm going to go positive feedback on you. All right? And I can get these two to flip around, and this guy's going to go that way, and this guy's going to come shooting through that way. But if it turns out that my specs tell me that I need to stay on this region, and these guys have moved out before this guy has crossed the boundary, I'm okay. All right. Dangerous design, by the way. Yeah.
So it's like in the root locus, like once you start moving the poles, poles repel each other and they're attracted to 0.
Right. So the zeros suck, the poles push.
Okay.
All right. That's one of the ways to. So things get sucked into the zeros, things get pushed away from the poles. All right. So the poles repel each other, everything goes sucking in towards the zeros. What's that? No, when you have positive feedback, you still go for, even with positive feedback, you still wind up going from the open loop poles to the open loop zeros. You just go in the wrong direction. Sometimes you flip around at infinity. So there's
One of the zeros got moved to positive infinity?
well, I switched this one, right? I switched this one around. So yeah, so one of the zeros went from negative infinity out to positive infinity. All right. When I flipped it around. All right. We'll do zero angle root locus later. It gets a little more involved. Yeah.
So the other thing is like in this case, the way that the 2 poles at 0 branch off is that.
We're going to get to that today. How you calculate the. Yeah, we get to calculate exactly what the angle is and where they follow and how to do it, and it's easy. All right. The departure angles are easy. So are the arrival angles. All right. No, you'll see. It's just extending what we already know about the phase argument, that the phase has to be 180, right? Or if I'm going positive feedback, the phase is going to be 0. Yeah, sure.
Next question, going back to the last slide you had.
Yeah.
What would happen if that 0 was closer to the origin than the settling time spec?
So if the 0 was closer to the origin, all right. So what I had was I had 2 poles. And I had a 0, and we had our settling time spec was out here. All right. If my 0 disappears and it moves to here, all right, then the root locus we're going to see, so still to the left, these two are still going to branch out at 90 degrees and orbit these two. All right. And so at this point, about the only spot I can get where this works is, right there, because as soon as they meet, one of them is going to go back in towards the 0. right? So I can only put them right as soon as they cross that line, right? And if I had some, and in this case, they're going to be there's going to be no overshoot. So, yeah, it'll be okay. All right. If this 0 turned out to be, fine. Go away, all of you. All right. If my settling time spec was here, and my 0 is less than halfway, right here, okay, now these two are going to go this way, one's going to split, the other's going to come out. Well, now I say, okay, I can't meet it without any compensation. All right. At this point, all right, I can make one of them go faster, but then the other one's going to be here. Now, this isn't going to have much of an effect because it's right next to a 0. Right? So a pole next to a 0 gets effectively canceled out. All right? So it's not going to have much of an effect on the response, but it also means you've got to be very careful there. It's not going to have an effect on the response as long as that 0 is actually there. If the 0 is, for instance, something you've added in your control system, all right, be careful that 0 is still there when, for instance, you're looking at a noise disturbance as opposed to your tracking, right? Because then all of a sudden that might not be there, at which point, having that there without a 0 there, well, that's, it's getting a nice, healthy response, right? And it's going to be too slow, all right? And you're going to say, well, my system's too sluggish, damn it, I need to speed it up, all right? So there's lots and lots and lots of trade-offs that you wind up doing. So part of it is just looking at where things are and what they are and what they're doing. All right. So with that as a kind of a nice refresher, let's go back to root locus. So rule 1 was I start at my open loop poles, and I go to my open loop zeros. That is, I go from the X to the O. And I showed why that was last time. I don't need to rewrite down the proof. That's rule number 1. Okay? And remember, open loop. Okay? Remember that it's the open loop poles and zeros that you do. This is why it's so easy. Because you remember that as you started adding feedback, the factorization started getting harder and harder because, frankly, if I made you do this and you had to factor an 8th order polynomial, well, you're going to run to a computer anyway. All right? Because there's not much else you can do. Right? I mean, I don't know anyone who can factor an 8th order polynomial in their head, so, unless it's really easy. Right? But if I've got a system that I've already sort of factored, I can add all kinds of compensation. I can just keep dropping it on top, and it doesn't matter, right? Because it's going to wind up multiplying back in. So it's okay. All right, so that's the first part. The second rule number 2, is points on the real axis to the left of an odd number of poles or zeros, right, are on the locus. Right? So what this says, again, if I've got 1, 2, 1, 2, 1, 1, 1. If I look at this, right, I can go along and I can say nothing, nothing, nothing. I got that, nothing. I got that, I got nothing. I got that. All right. And I can actually start to see, just with rules 1 and 2, all right, I can start to see where things are going. Now remember, the root locus gives you all of the possibilities of where the roots of the closed loop system can be. All of them. All right? And then by choosing your gain, it tells you where on the specific one that you pick. Right? But I can tell you that this pole is going to move towards that 0. Why? Because the zeros suck. Right? So it's going to move into this 0. Right? And in fact, I can actually figure out exactly what gain will push this system unstable. Right? Because as soon as that pole crosses that line, then we're unstable. Okay. Likewise, I've got these two, and I say, this is going to be interesting. What's going to happen here? And most likely what's going to happen here is we're going to see that these two are going to pop in. One's going to split and go to one. The other's going to split and go to the other. And then these two are probably going to do something where they're going to split. They're going to go up. They're going to get sucked in towards the 0, and then they're going to wind up on an asymptote going out to plus or minus infinity at 90 degrees. Why is it at 90 degrees? Because I've got 1, 2, 3 poles. Sorry, 1, 2, 3 zeros. 1, 2, 3, 4, 5 poles, which means there are 2 poles more than there are zeros, which means that there are 2 zeros out at infinity. And in this case, they can't be on the real axis, right? Symmetry applies, so therefore they're going to be out at j omega. Right. We're going to do the asymptotes right now.
Does it need like infinite frequency to drive the system unstable for those 2 poles at least?
Well, you'll drive it unstable with this one first,
Right.
and what you'll see is as you start cranking up the gain, right, what you'll see on the response is these two aren't going to do much because they're going to be close to the zeros. This one is going to give you a slower and slower rise time, right, because this is a sluggish, sort of very slowly climbing up, and as soon as you get past that point, it's actually going to diverge and start just climbing cleanly away. These two are going to show a very fast oscillation, and the more you crank it, right, the less damp that oscillation is going to be. But they're always going to damp out, right, because these can't move into that plane. Okay? All right. Let's do the all right. I think this is the one I'm on, but I'm not sure. I could be missing one. No. There we go. Okay. That was why that one was there. All right. So we've done... All right. So the next rule is rule number 3. And rule number 3 says asymptotes. Okay? And this is the number of asymptotes is n minus m, where this is the poles, and that's the zeros. So the number of poles minus the number of zeros tells you the number of asymptotes that you have. The angle, or rather the center of the asymptotes, is the sum of the poles minus the sum of the zeros divided by the number of poles, excess poles over zeros. Okay. And the angle that they're at is 180 plus 360 L minus 1 over n minus m, where L goes from 1 out to n minus m. All right? Now, so let's do a simple one. All right? Here's the, let's say I've got, so I got a complex conjugate pair, right? So an oscillatory pair. Right. I've got a 0. Well, let's keep it all. Bad. So here's my system. Okay. And by the way, you should be able at this point to write the transfer function by inspection. At this point from this, all right? Because that's a s squared plus omega squared. Right. That's an s plus a in the numerator. That's an s plus b in the denominator. Sorry. So I go through and I say, hey, rule number 1 starts at the x's, goes to the o. That's the easy one. Rule number 2 points to the left of the real axis of an odd number. All right. So I'm going to go through and I'm going to look along the real axis. Here's an odd number. And there it is. So that one starts there and goes there. Now, these two are going off somewhere, but they're not going on the real axis. Okay. So I now say, all right, where are the center of the asymptote. So first of all, I've got 3 poles, 1, 0. That means I've got 2 asymptotes. Right? So I've got 2 asymptotes, so n minus m is equal to 2. Okay? The center, let's call this one, let's make life easy, minus 1, minus 2, and these, of course, are 0. All right, so this is going to be 2 times 0, right? That's easy. Right, 2 times 0 plus 1 times minus 2, so 0 plus 0 plus minus 2, so that's minus 2, right? Minus, so it's minus 2 minus 1, right? There's one of them, divided by 2. So it's minus 2 plus 1, so minus 1/2. So right here, okay, is the minus 1/2. Okay? The angle, right, is going to be 180 plus 360 times L minus 1, the whole thing divided by, right, so 180 divided by 2 is 90. If I add 360 to it, I get 270 or minus 90. Right? So the angle is equal to plus or minus 90 degrees. Right? So I've got an asymptote that's like that. And the only thing left to determine at this point is what do these guys do as they leave and get on this asymptote? Do they do that, or do they do that? You know, whichever one they do. I have to figure out where they're going. All right. But once I know where they're going, if they do this, if they do the first one, for instance, if they do that, I say, now, we're going to see the next rule I'm going to show you after we prove why these apply. The next rule I'm going to show you is how we calculate the departure angles, all right, and likewise the arrival angles. All right? But once I have the departure angles, all right, I'm going to go through here. But assuming I find the departure angle and they're going out this way, and so I say, okay, at some point they got to get on this asymptote, which means they're crossing back across the j omega axis. All right, and how am I going to find that? All right. Well, it's pretty easy actually. All I'm going to have to do is search until I find that I'm going to search along this point until I find that the phase is equal to 180. Right? And that's it. Right? So I'm just going to do this. I'm going to find 2 angles. And I'm going to move up and down. I'm going to find it, you know, at what point the phase of that point equals 180. Then I'm on the root locus. Right? And I can find exactly the point at which, exactly the gain at which I go through. Right? I find the point. Once I find the point, divide by the length, and I'm good to go for the gain that gets me stability. Yeah.
I don't see how an angle of plus or minus 90 degrees would use that drawing. Looks like they're going out like 45 degrees or something.
No. The angle is of the asymptotes. So, the asymptote, not the departure angle. Ignore the departure angle for now. That's the next rule. That's what we're going to do, departure angles. Okay. So, let's see why these are the way they are. Okay. So, the first one I want to talk about is interesting. Oh. Very interesting. Okay. So I want to write down trying to figure out which page of notes I'm on here. Okay. Let me write down for a characteristic transfer function. I'm going to have some very generic s to the m plus b1 s to the m minus 1 plus all the way out to, I'll do a couple more terms. The book does probably a better job of this than I'm going to do, but all over s to the, oh, that's an m, by the way, s to the n plus a1 s to the n minus 1, all the way down to all right. A2 s to the n minus 2, all the way down to a to the n. Okay. Now, hopefully you guys remember this. If I have s plus a1, s plus a2, or let's call these, and s plus a3, all right, and I multiply this out, I'm going to get an s cubed plus, does anyone remember what goes in the s squared term right here? Yeah, a1 plus a2 plus a3, right? Right. So if I look at this one here is the sum of the poles, and this one here is the sum of the zeros, right? So if I go from my poles and zeros into my long polynomial, right, this term is the sum of the poles, rather, this term is the sum of the zeros, back, and this term is the sum of the poles, right? So what I'm going to say here is the reason we're trying to get to the asymptotes is, imagine, so I'm going back here, zoom way the hell out, right? So that your first tick on your graph is 100,000, all right? You're not going to see anything here, right? All you're going to see is, as far as you can tell, there's going to be two poles right on top of each other. You're not going to see the pole and the zero. You're just going to see this clump of poles in one spot, right? Any sort of niceties about, well, these are up on the j omega axis, that was, you don't see. They're right there. Right? They sort of come down to one clump. And from far away, that one clump is going to split and go in a symmetric pattern outwards. All right? So what we're trying to do is figure out from far away, what does that clump actually look like? All right? Which gets us the center of the asymptote, all right? And then we'll get to the angle. All right. So when I look back at this and I say, hey, for really big S, all right, I'm zooming way out, this is going to look pretty damn close to, that ratio, right? I've got S to the m over S to the n is going to look pretty close to 1 over S to the n minus m, right? In other words, the zeros and the poles are, as far as I'm concerned, as soon as I get far away, they're on top of each other, and the only thing that's left is the residual poles that have no zeros attached to them. Okay? All right. Now, what I want to say is that I want to look at this. I basically want to substitute for this something that looks like 1 over s plus alpha to the n minus m. Right? So I want to say this is approximately equal to s to the m plus b1 s to the m minus 1 all the way out to bm all over s to the n plus a1 s to the n minus 1 all the way out to a to the n. an rather. That's b sub m and that's a sub m. n. All right? So this is what I'm doing. I want to look at, I'm saying that this, from far away, for big S, is going to be very close to that. And so I want to know what this alpha is that gets me there, right? That gives me my best approximation. And so all I'm going to do here is, shockingly, long division. So, as I said, we wouldn't be doing it if it wasn't easy. So I'm just going to take, so see, here we've got s to the m plus a1 s to the, so this is n in here. n minus 1 all the way down to s to the an, rather. And I'm going to divide this by, whoops, this is, yeah. And I'm going to divide this by s to the m plus b1 s to the m minus 1 all the way up. So the first one I'm going to get is s to the n minus m. Okay, that's the first term. Right? And when I do this, what I'm going to have underneath here is s to the n plus b1 s to the n minus 1 going out this way. And when I subtract this off, what's left as my residual is going to be a1 minus b1, right? So this is going to be plus a1 minus b1 s to the n minus m minus 1 plus more terms out there. So what that means is n minus m times alpha is going to equal to a1 minus b1. Yeah? And which is, says that therefore the alpha is equal to, well, it's the sum of the poles minus the sum of the zeros divided by n minus m, which gets us there. All right, now, important thing to remember is that on the root locus, symmetry always applies. All right, the root loci is always, always, always symmetric. All right, so basically the angles that I find, I can usually do by symmetry argument. All right? So what that says is, if I have, let's say I give you 1, 2, 3, 4 poles right on top of each other. Okay? So they're going to be symmetric. All right? And by symmetric, I mean symmetric about the real axis. All right? So there are only 2 patterns, all right, that are going to give me that symmetry. All right? One is that they go off like that, right? And the other is that they go off like that, right? Which one does it have to be? Thank you for trying. Do we have another player? Why can it only be the red ones? What's rule number 2 about the real axis? Only to the left of an odd number. There are no odd numbers here. Right? So therefore, it can't be on the real axis. So the only one left is this other one. Right? Same thing if I've got 3. Right? So I have 1, 2, 3 right on top of each other. Right? So to be symmetric about the real axis, they're either going to go out like that, all right? So this is symmetric, right? Or they're going to go like that. All right? Well, it's going to be red, all right? Because the green one is verboten because of rule 2, right? So, and this is going to be 60 degrees. That's going to be 120 degrees, 120 degrees, and 60 degrees, minus 60 degrees, right? It's symmetric. It's always symmetric, right? So the number of poles always divides the circle into even sectors, right? And it's always symmetric about the real axis. So the number of limitations there is actually quite small. You can use the formula if you like. The formula works perfectly well. All right. I just like to understand what the formula is actually telling me.
Can you explain why green is no good but red is?
Because I have to have, according to my root locus rules, all right, I can only have, the real axis can only be on the locus to the left of an odd number. If I've got 3 poles here, then this part is on the root locus.
Okay, and green would change that around.
And green would say that part isn't on the root locus, this part is on the root locus. It has to stay on the root locus. Right? And therefore that's why the asymptotes split apart. So the asymptotes are from far away. These things are shooting off to infinity in a symmetric pattern. How are they doing it? Right? So they start from the center, alpha, right? And they go off these asymptotes, and they eventually line up on these asymptotes and spin off to infinity along those asymptotes. All right? So that gives you sort of a very good idea. Now, the one last piece that is missing, right? So, by the way, this one would be a 1 over s plus a to the 4th. All right? Just so you know. All right? N minus m here would equal 4. All right? Alpha is going to equal to minus a. And the angle, right, is essentially it's 180 divided by 4. Right? So 180 divided by 4 is 45, right? And then 1/4 of the way around the circle for each additional one. Right? So the first one is 45, then 135, then, well, I just go negative 45, and then minus 135, right, to get you around. Right? That works. The formula works perfectly well. I just like to understand what the formula is telling me rather than going off, and just applying it blindly. All right, that always makes me feel better. All right, I like to know. Okay, so now we got one last one. Okay, so this one is rule number 4. Okay, and this is the angle of departure or arrival. Right? And you can do both of them the same way. All right. So, for instance, let's go back to my original that we had. We had 2 here, 1 there, 1 there. Okay. And I can tell you from the real axis, that one's on. We found out that this was the asymptote, plus or minus 90 degrees, and that this is somehow going to wind up on there, but we need to know how it leaves, right? We need to know the departure angle. Okay. There's a formula for it in the book. I find the formula basically a poor way of doing it, so I'm going to teach you a different way of doing it, which I find much, much better. Okay? And that is that I'm going to put my sample spot that I'm going to take. Remember that the whole thing behind this is we're looking for a phase of 180 degrees. Right? So I'm going to put a little dot on here that's on the root locus, but that's epsilon away from that pole. Right? So it's right on top of it, but it's on the root locus. All right? So this is whatever the departure angle is, right? That point is on the departure, right? Just right next to that pole. Okay? So now all I'm going to do is evaluate the phase at this test point. Okay? And what is the phase of this test point going to be? From this pole, right, I've got 90 degrees. Right? So I'm looking at the ray from what is essentially right on top of this pole down to this one. Right? I've got 90 degrees, but it's a pole, so it's minus. Right? So this one is also, so let's start here. I've got phi departure negative away because from this pole right here. Right? That's my angle away from there. I think I've lost all of you. Okay. No, I haven't lost you. You're perfectly good with this. Okay. I have this little point right next to it that's on the locus. Right? So it's on the locus. That means the phase has got to be 180 degrees. Okay? That is it's on the locus, and the locus left here at the departure angle, phi d. Right? It's from a pole, so it's negative. Right? So the phase of this little point from this pole is minus phi d. Right? From this one it's minus 90, right? It's normally 90 degrees, right? But it's a pole, so it's negative. So it's minus 90, right? This one, all right, let's make this 2. That was minus 1, all right? So this one is what? 2 minus 1. Let's make it 1, make life easier, okay? Minus 1, minus 1. So that one is 45 degrees, right? I'm on top of this pole, so it's the same. I'm just measuring the angle to that pole. Well, that's 45 degrees, and it's a 0, so it's plus 45 degrees, right? And this one, all right, is arctangent of 2, right? 1/2, right? So arctangent of 1/2, 1, 2, right? So that's about 26 degrees, I think. Pretty close to it. All right. And it's a pole, so it's negative. Minus 26 degrees equals, the sum of all the phases has to equal what? Plus or minus 180. Okay? So this is plus or minus 180. Right? And so now I go ahead and I just, pick plus or minus, do the addition. I'm going to find phi d in this case is equal to 109 degrees. Right? So what does that tell you? 109 degrees. So I start here and I go, there's 90, right? So 109 degrees is, it's roughly going that way. Right? So now when I draw this root loci, right? So I started here as 1. So I have 1 here, a 0 there, 1 there, there's a 1/2. Okay, there's 1 there. What this is this one goes that way. These two leave. This one leaves at 109 degrees. This one leaves at minus 109 degrees. And they both go along to the asymptote. All right? Now, I can also, by the way, do the arrival angle. This one's going to be a little easy, but I want to know it. All right? Assume that I didn't know that this was just coming straight along the axis, and I wanted to know it. Let's figure it out. All right? So phi arrival, all right, is again, I'm going to take this little point right here. It's on the loci. All right? And so I got phi arrival, right? That's that one. It's positive because it's from a pole. I've got 180 degrees, right? Well, this one is actually, so I look at, the angle that my ray makes with the horizontal is 0 here. So that's minus 0 because it's a pole. I've got this one, right? So the angle I'm looking at here is that, right? That angle is 180 plus 45, all right? Or I can minus that one, which is, 135, but it's a pole, so it's negative. So it's going to be minus 135. That one's going to be plus 135, right? Equals 180. Right? Well, those two cancel it out, so phi a equals 180 degrees. It's coming in from here. This always works. Right? Regardless of how complicated or nasty it gets, this always works. Right? And this is kind of cool because it's a fairly intuitive and easy way to do it. Right? You just stick a dot right next to your thing and just add up the phase of everything, and it's in its static case. Right? It's everything is just on top of the polar 0. Right? So all you're doing is working out the fixed geometry of it, adding up all the phases until you get to 180. Same thing if you have zeros. Now, we can do this for really, really complicated systems. So here's one we'll do. Let's see, I've got. Let's do 1, 2, 3. All right, and another one here at minus 1. Okay. So let's start.
Before we start this one, I have a question about the previous one.
Yeah.
Instead of looking for a little point that's an angle PD from one of the roots you picked,
Yeah.
and that point is going to be on the root locus. Like
No.
on the root locus.
You mean on this one here?
The previous, when you're doing the departure angle.
Yeah, when I'm doing the departure angle, so I'm going to pick a point on the locus that's epsilon away from this pole.
What do you mean by on the locus? Can you explain that a bit more clearly?
That means that the phase of that point adds up to 180.
Okay.
Right? That's what it means to be on the locus. Right? That means that the root is going to move. The closed loop pole is going to be moving along that line. Right? It starts at the open loop pole. It's going to move along that locus, going to infinity. Right? I need to know where it. I'm trying to figure out where that locus is. Right? I want to know what angle this pole leaves, where it departs from. Right? I know it stays here, but it's going to leave from there and go along a certain angle, getting to the asymptote.
The register is a shortcut on the real axis.
So, okay, I see. Because that's what I was thinking of the root locus. So the thing's on the real axis. So that's just one of the root locus.
That's one branch of the locus. There's also, I mean, for every pole, you actually have a locus that's moving, right? Every pole moves, right? And it may be moving very, very slowly. This one's going to start because remember, this pole is going to reach that zero at infinite time, right? Infinite gain. It's going to be on top of it. But so it's going to start out moving and it's going to start slowing down as it gets closer and closer, right? So it may not be much of the locus. It might not be moving much. Whereas these two guys are going to be screaming out towards infinity as you crank the gain up.
So the correct interpretation of the locus is a path that one of the poles follows as the gain is changed?
That's correct. Okay? And to find that path, we're searching the complex plane for areas where the phase adds up to minus 180. Why are we looking for the phase that adds up to minus 180? Because we put it in Evans form where we said that k n of s over d of s equals minus 1. All right? And minus 1 has a magnitude of 1 and a phase of 180. So since I've got k to set the magnitude, all I'm searching for is a phase of 180. If I can find a phase of 180, I'm golden. All right? That's all of this is. All right. So as an example, let's start with the one I've got. Let's do 1, 2, 3 at the origin, nothing else. All right? So we start with our first step. Okay? And our first step says, well, poles to zeros, yeah, we already knew that. Okay. Start with rule 2 is the real axis. Okay? So real axis says to the left of the 3, I'm on the real axis. One branch of the loci, or one branch of the locus, I don't even know which. One branch is going along towards minus infinity. Okay? 2, I say asymptotes. In this case, alpha is 0. All right? The number of them, n minus m, is equal to 3. And therefore the angle is going to give me, now I know that symmetry applies. It's going to be 360 is going to get divided into 3. All right? So, which way is it going to go? It's either this way and that way, but it can't because that one's on. So I've got my asymptotes, and that's 60 degrees and minus 60 degrees. All right? So plus or minus 60 and 180. All right? So I've got my asymptotes. Now, the last thing I need, so I know that sort of by the time we're out here, these are on the locus. But I need to know what angle they actually depart at. Okay? So to get my departure angle, right, I'm going to put a little point on the locus, all right, and say this one's going to be, so there's 3 poles. This is minus 3 times the departure angle, right, because I'm getting 3 poles at the origin, my little departure angle, right, so it's 3 times that departure angle, negative because they're poles, right, plus, well, there ain't nothing else, is equal to minus 180. All right? Or I can use plus 180. It doesn't really matter. Right? Plus or minus 180 will give you the same answer. All right? You just have to remember that symmetry applies and just remember which one is which. Okay? So I do this and I say, hey, phi d, therefore, is equal to minus 60. All right? And I say, okay, that's, what do you know? They go out right along the asymptote. Okay? So these 3 punch off right next to the asymptote. Okay? So now someone comes along and says, oh, that was nice, you did a good job, but I'm going to mess with you a little bit here. I'm going to say, you have your same 3 that you thought you had. So there's your 3 poles. But you got another one out there at -1. Okay? So again, we're just going to go through and do it. And we say, all right, no problem. Let's figure out. So first of all, real axis. All right? To the left of 3, yep. To the right of 4, to the left of 4, nothing. All right. So something is going on here. All right. So 1, real axis. That was easy. 2, asymptotes. All right. I've now got -1 divided by 4. All right. So n minus m equals 4. Alpha equals -1/4. So here's my center of balance, essentially, of these guys. Right. Which, think about it. You know, this is the fulcrum. I got 3 on that side and 1 on that side. It's going to balance 1/4 of the way over. So this is why, you know, think of sort of hanging weights on it and figure out where you have to support it to get it to even out. All right. So it's right there's the fulcrum. Okay. So there it is, -1/4. And the angle of the asymptotes, right? In this case, right, it's going to divide a circle into 4 equal parts. So either it's up, down, and along that, but I can't do that because the real axis isn't there. So I can already tell you it's going to be at 45, you know, 45, 135, -45, -135. I can go ahead and use the formula. It's not, right, 180, what is it, plus 360 L minus 1 divided by n minus m, which in this case is 4. All right? So the first one, 180 divided by 4, 45. All right? So I've got 1 asymptote, 2, 3, 4. All right? Now you say, okay, how are they going to get here? Okay? All right, so now I need to figure out what my departure angles are for, let's start with these 3. This one I already know. I mean, I can calculate it, but I already know the departure angle for this guy is going to be 0 degrees, right, because he's flying in towards that way. He has to because he's on the real axis. Likewise, one of these 3 better work out to be 180, or I've got a serious problem. Right? So one of these 3 has got to go towards 180. Okay, so here's my departure angle, right? Epsilon away. I've got, again, -3 phi d, right? 3 because there's 3 poles, negative because they're poles, right? And phi d because I'm on the locus. Okay. Minus, because I've got this one, well, the angle to that one is just 0, right? Is equal to -180. All right, so I've got the phi d is equal to, this one's going to be 60. Right? I've also got, I can put a plus 180, so I get -60. Right? And I can, of course, add 360 to that. Right? So I can say, hey, I'm going to do 180 plus 360, which is going to get me 180. Right? So there are my 3. Right? So I now can say, hey, I now know my departure angle, right? Which says that one of these guys is at 60 degrees, the other is at -60 degrees. So 2 of these are going like that, right? And this angle is 60 degrees, and that angle is -60 degrees. So what's that mean? That means that these 2, one that's going this way and the other that's coming this way, are going to meet up in the middle, right, somewhere. And they're going to split off and go somewhere like that. Right? Now, the exact point at which they split off, we can find. That's another rule. It's one of the ones I'm actually the least fond of. And the reason I'm the least fond of it is because you wind up having to take a derivative of your transfer function to do it. And if you're already taking derivative of your transfer function, then you're probably close enough to firing up the computer, at which point it doesn't matter anymore. Anyway, but for simple systems, it works out okay. All right, so let's just do one more. And so what we've got here essentially are the outlines of a procedure, right, of how we do this. And where I'm going to want to go with this, we'll go over it a couple more times so we see what's happening. And then what I'm going to do is I'm going to do an example of a system. We're going to analyze it doing root locus. We're going to show sort of what happens, put the gains where we want such that we get the right kind of compensation, and then show what happens as we start messing with the system. We say, well, you thought you knew what the system model looked like. In fact, you didn't. There was an unmodeled higher frequency mode that you were not aware was there. And what happens when we bring it back into the model to see sort of how it affects and how the tools that we have can do this. For now, let's just do, so the procedure is, 1, we do the real axis. 2, we do the asymptotes. 3, phi departure, phi arrival if they exist. All right, and that's usually pretty close to where, and then you sort of sketch it in. All right, and after you do enough of these, there's going to be certain patterns you'll see over and over again. So, for instance, if there are 2 poles and a 0, right, what you're going to find is that these poles go along an orbit that is defined by the radius away. All right, and so these will just orbit around until they hit, and they'll split. One will go in, one will go out. All right, and there's going to be certain things that you'll see. You'll see things like when you've got, for instance, 2 poles that are going to split here, and there's another pole and there's a 0 there, these 2 will do something like that. All right. Why are they doing that? Well, they're getting pushed away by the pole that's there, but then they get sucked back in by the 0, and then they eventually wind up on their things. Let's just do one, a real one. We've got like 1 minute left. I have plenty of time for a root locus. Okay, so let's do one where I've got, let's put 2 poles at the origin. Let's put a pole and a 0 here, and let's put 2 zeros up here, and we'll put another 2 poles up here. All right, and we're saying, hey, this is, now we're getting something complicated now. All right, this is a nasty, hairy transfer function. All right, this is 1, 2, 3, 4, 5. There's an s to the 5th in there. All right, at least. Okay, and you've got at least an s squared up in an s cubed up in the numerator. All right, we're getting there. All right. So now, first thing I'm going to go is along the real axis. Okay. That pole is going to move straight towards that 0. Okay. Now I say, okay, no problem. I'm now going to look for asymptotes. All right. Let's make my life easy to calculate and put these right there. All right. Just because I don't want to have to solve any algebra here, or trig as the case may be. And I say, okay, real axis done. Asymptotes, I've got all these zeros. I've got this one. Let's say this one's at -1. Let's say this one's -2. All right. So I've got -1 minus -2 is +1. Right. +1 divided by what do I've got? 1, 2, 3. 1, 2, 3, 4, 5. So +1 divided by 2, it's at 1/2. All right. So here we are at 1/2. Here's my asymptote. Okay. Now, do the departure angle. All right. Put a little dot here. Figure that departure angle out. Put a little dot here. Figure that departure angle out. Put a little dot here. Figure that arrival angle out. All right. So one of the things you need to know is this, right? Does this do this like that, or does it do that? Okay. And then these 2 are probably going to do something like that. Right? Now, maybe I'm completely wrong, right? Maybe these 2 come in towards there, and these guys go out towards there. Right? That's actually not that different, as it turns out. Right? Anyway, we'll continue to play with this on Tuesday, and I'll see you guys then.